Just going to wait for anyone to come in. Quite often I wait for someone to come in, so anyone who's here who notices a awkward pause, that's because I'm waiting for people to come in. But in the meantime, okay, I think we do have some people in the lobby, in the waiting room. All right, so put thumbs up in the chat if you're here, just to let me know, and we can probably get started. The thumbs up in the chat. Thumbs up in the chat. Anyone with a thumbs up? Okay, I think we're going to get started anyway. So welcome back to STEM Online Academy. My name is Jason Masterakos. For those of you who don't know me or what STEM Online Academy is, let me remind you. So first off, I have a background in advanced mathematics and physics from Carleton University. And also STEM Online Academy is exactly that. We specialize and we're all about teaching unique ways to understand advanced mathematics and physics to help facilitate undergraduates' mathematical intuition. Okay, so mainly for an undergraduate audience who is curious about learning more in mathematics or needs help facilitating a certain level of mathematical maturity. Okay, what does that mean? That means being able to have a stronger intuition when it comes to solving advanced math problems, and the same for physics as well in physics courses. All right, so let's get started. So for those of you who don't know, for those of you who already have watched my previous videos, you already know pretty much my style of doing things. It's just we either talk about one concept or two problem solving. Okay. Now, some of the concepts we'll discuss, maybe not in the last couple of videos, but in the future will be very interesting. Okay. Either due to might be on cool physical or mathematical phenomenon. But lately we're looking at problem solving. Mainly my videos have been on problem solving and pretty much pertaining to my book, Advanced Integration Techniques. The last couple of videos have been on that. It's pretty much a mathematical methods book, which is for an advanced audience, again, for undergraduate students. As long as you have a background in calculus, linear algebra, this book will be, you'll be able to follow. Okay. So last time we did some interesting stuff on Fourier transforms and Gaussian integrals. Actually, that was the time before. Well, last time was introduction to contour integration. Okay. So if you haven't watched the last video or live video, it'll be handy to look at that. Even though for this one, it's not necessary. Today, we're going to talk about another integration method called Feynman Trick. Okay. And it will also not only be on Feynman Trick, this live show, I'm going to engage with the audience. In other words, you guys can ask me your hardest integral problems, and I'll do my best to solve them. So any integration problems you have trouble with, either from your studies or things that you've taught yourself when you're interested in solving them, post them here, and I'll be able to solve them to the best of my ability. All right. So let me open the whiteboard. Okay, let's see what's in here. Okay, let's get to the whiteboard. All right, just 1 second. I have to share my screen. All right, so we're getting to the whiteboard here. So anyone in the chat, hopefully you can see what's on the whiteboard. Okay. All right, so what we're going to be looking at, as I just mentioned, it's going to be an open problem night. Pretty much viewers will be able to send in hard integrals or whatever you consider hard, but preferably like really tricky ones for me. But send in any integrals that you're having trouble with. Okay, so it's going to be a back and forth ask Q&A type of live show today. Question and answer when it comes to integration. Okay, so any type of hard integral, please throw it my way. If you have trouble with it, don't be shy. And at the same time, we'll be looking at something called the Feynman actually, this is not technique, Feynman trick. Okay, this will be handy for a lot of undergraduates, actually. Okay, Feynman trick for integration. Okay, Feynman trick. Sometimes they get technique wrong. It's not technique, Feynman had something else. All right, so let's get into it. Right, so as I mentioned, we're going to look at the Feynman trick and parameter differentiation. Okay, it's probably new for a lot of you. For those you already know about like Feynman trick and how to integrate things, you will enjoy this live show. Number 2, how to analyze integral families. Somewhat nothing particular that I need to get into, but yeah, we might look at that. I think some of that will be axiomatic as we're going through the problems. 3, I'll have to talk about separately complex logarithmic substitutions. 4, when to invent new special functions. And finally, collaborative open-ended exploration. If anyone has problems, as I said, you can ask me at any time. You can interrupt me. It doesn't have to be at the very end. All right. Anyone in the chat, put something in the chat, please. Thumbs up or anything. Okay. Might be slightly still early. Usually I notice in Wednesdays, the audience comes a bit later. I think it has to do with the time zone variation. Depending where you are, maybe if you're in, Europe, Asia, or anywhere else for that matter, right? So time zone would be depending on you. Anyways, let's get started. So I want to mention something called the Feynman trick. We haven't discussed Feynman trick yet. Okay. So this method is in my book. Okay. And it's a way to solve integrals, complicated integrals, right? This is not elementary integrals. This is for complicated integrals that can't be solved using elementary methods. Okay, as I said, as long as you have integral calculus and linear algebra as a background, you should be able to understand exactly what I'm talking about. All right, so let's get started. So definition, Feynman's trick is a method for evaluating difficult integrals, right, by introducing a parameter. This parameter, you can call it whatever you want. It can be A, B, C, alpha, beta, gamma, doesn't matter what it's called, as long as you introduce a parameter, okay? And then you need to differentiate the parameter. Okay, so then you're going to have to differentiate the parameter of the integral with respect to that parameter. All right. And then once you differentiated with respect to the parameter of that integral, then you have to integrate back to get a resulting simpler expression. Okay. I want to make sure everyone's understanding what I'm talking about. Okay. Let me know if there's any issue in the chat. Okay, I'll repeat again, right? Feynman's trick, right, is a method for evaluating difficult integrals. By the way, Feynman was a theoretical physicist, okay, who is responsible for a lot of things in physics, actually, things in quantum mechanics and electrodynamics and stuff like that. Yes, a lot of stuff, but he also made a contribution to mathematics as well. And this is his contribution. Okay, it's evaluating very difficult integrals using a very clever technique or a very clever trick, right? So that's a little bit about Feynman. So his trick is a method for evaluating difficult intervals by introducing a parameter, right? That just means a variable. And then differentiating the integral, right? Because obviously it's an integral every time. So we want to differentiate both sides of the integral with respect to the parameter that we chose. Okay. And then integrating the resulting simpler expression. Okay. Anyone have questions? Anyone lost or anything? Okay. Just don't be shy. Anyone who's here, just put something in the chat. Don't feel shy at all. Okay. Just want to make sure it's coming in. Coming in. Just waiting for people. Sometimes I don't know if I should wait or continue with the live show. I'm going to continue talking. Okay, so what is Feynman's trick exactly? So I gave you somewhat of a definition of how to do this technique. Now, more formally, okay, the formalization of this, let's call capital I some integral. Okay, so I'm going to call variable capital I as a function of a. Okay, a will be the parameter. Okay, so a is the parameter. Okay, so a is some parameter. And we've defined our integral from a lower bound of x0 to an upper bound of x1 of a function of x and a with respect to x. Okay, so we take a regular integral, that's a function of x and a now, right? Because we're treating our new parameter that we've defined as a. Okay, so we have two, it's a function of two variables, the variable x, as you all know, and a variable a, the parameter. And then we, with respect to x, okay? Where f of x comma a, and I'm going to say di f di a, that's a partial derivative. Those of you, even if you don't know what partial derivatives, if you know derivatives, partial derivatives will be very easy to calculate. Okay, so di f di a are continuous in both variables. Okay, so continuous. All right, so there's no jumps, there's no discontinuities. It's purely continuous. Okay, you guys should know what continuous means. Okay, so the definition of continuous, right? Okay. All right, so anyone have questions about the definition of continuity? If we need to go back to that, no, I don't think so. All right, so our continuous in both variables. Then Feynman Trick states the following, right? So we take the formal integral as a function of x and a, okay? Are continuous in both variables. Then the Feynman Trick states that the d by dA, right, of an integral I as a function of a is equal to d by dA, right, of the integral as a function of x and a with respect to x, okay? All right, and then this is equal to the integral of from x0 to x1 of di a of f of x comma a with respect to x. So as you can see here, I'm just taking the words, right? The formalization and putting it into an equations, right? As I mentioned, right over here, right? The function that we're dealing with, I of a, right? We just differentiate both sides with respect to the parameter a. That's all we're doing. D by dA by a is equal to d by, or you can say on this side, it's the same thing, integral from x0 to x1, di a of f of x comma a dx with respect to x. Okay, that's when we implement the Feynman trick. Now, for those of you who are here, I have a question. Well, at least the ones that know this. The Feynman trick is related to some other type of method. If anyone knows, the guy's name starts with an L. This is a trivia question. Okay. Everyone likes trivia. Okay, so we have a d by, so we have Feynman here, right? Feynman's trick for evaluating complicated intervals. Okay, it looks very familiar, actually. All right. So I'm going to wait for anyone in the chat to either respond or come in, give you guys some time, and I'll repeat the question anyways. So again, right, what we have here, right, is a Feynman trick, right? So Feynman's trick is this nasty equation here, okay? But it looks familiar. It looks familiar to something some of you may have seen before. It's called Leibniz's method, okay? So Leibniz's method is mainly, is this: differentiating both sides of an integral to recapture the integral and then solve for the original function. Okay. The only difference between the Feynman trick and Leibniz's method is that with Feynman's trick, Feynman came up with a clever method where you can input a parameter in the right place of the function. Okay. Right? Whereas Leibniz was automatically, he was just doing it, I guess, intuitively somehow. He was just able to, he knew that if you differentiated both sides of the integral, you get back to the original function, right? Feynman says exactly the same thing, but the only thing is Feynman does it cleverly by inputting a parameter, A, or whatever you want to call your parameter, right, in the correct position of your function, such that when you have to differentiate both sides with respect to the parameter, it's easy to integrate afterwards. Okay. All right. Is there any misunderstanding on that? Okay. Right. So again, with Feynman, his trick, you have to be careful. You have to invent a parameter and place it in the right position of the function, such that when you differentiate both sides of the integral, you get back to you'll be able to integrate that function after you differentiated that with respect to that parameter. And when I mean be able to integrate, I mean you have a method, a mathematical method for integrating it. Okay. All right. So I'm going to show you some stuff soon, right? But as I mentioned, this trick lets you introduce a parameter A into a very difficult integral. Now I want to, so I have to be careful, right? It lets you introduce a parameter A into a difficult integral. It doesn't work for every integral. There's multiple methods for evaluating complex integrals or advanced integrals, whatever you want to call them, right? You just have to see if they fit a particular form to decide what method to use, if that makes sense. Okay. Quite often they need to be put in a mathematical form, a certain mathematical form, because otherwise they don't work. In other words, quite often, I'm sure you guys noticed in your math classes, right? You need to manipulate or add or do something to the problem or the equation in order to get it into a particular mathematical form. And once it's in that form, you can apply certain definitions, theorems, or whatever, right? Or formulas. Okay. Anyone have questions? Anyone have questions? Don't let me hanging here. Questions are good. Don't be shy. Put something in the chat. All right. Okay, so let's see here, right? So we're continue talking about Feynman trick. So introduce a parameter A into a difficult integral, right? That's number one. Number two is that you always have to be able to differentiate the integral to obtain a simpler one, as I mentioned, right? You want to differentiate that integral in order to obtain a simpler integral, an integral that you can actually integrate and is not completely messed up. That's pretty intuitive. It would be pretty straightforward what that means by simpler. Okay, the number three, once you've done that, once you've integrated that simpler integral, okay, you get back to a particular form. You want to simplify that form as much as possible. And then step three, integrate again to get the simpler result with respect to A. Okay, so you want to integrate again back with respect to A. And then from there should be a step four. I didn't have room in this page. Four is just solving using boundary conditions. Maybe explain that a bit later, but anyways. Okay. All right. So we've covered the Feynman trick. Anyone have a question on the Feynman trick? Anything about the Feynman trick that is a bit complex? So far, I'm just talking theory right now. I know. Okay. Last couple of videos I've been talking mainly theory for quite some time. I have to, because otherwise you have to understand how to do it before you can do it, if that makes sense, right? The theory is more important than the problems. The problems are just whatever, right? It doesn't matter how many problems you have, what type of problems. You just need to make sure that you understand the theory very well. And it doesn't matter what problem they give you, whether from very easy to very hard, you'll be able to tackle it. So understanding the theory makes the most sense to do when it comes to math. And the best way to understand the theory is to make sure you understand per se what it's actually saying, right? Okay. Like, look at this, right? So like the definitions, yes, they're blocks of paragraphs and everything, but you have to make sure you understand what you're reading, right? Because if you don't understand what you're reading, then it's going to be a problem, right? Then all of the problems are going to be a problem. Funny. That was a pun intended. All the problems will be a problem. Okay. So yeah, it's very important to understand what you're reading. Okay. If you have trouble understanding it at first, read again, or partition what you're reading. Like take phrases and try to make drawings. Sometimes drawings can help you step by step, like from one phrase to another phrase, another phrase. Make drawings and make a total set or a total drawing of what is being asked. So take the words and then translate them into a visual spatial type of approach. Okay. If you watch my other videos, you'll know that that's quite often my technique. Okay. All right. So we're going to look at applying this approach, the Feynman trick. Okay. And we're going to use it on a on a an integral that can't be solved by elementary methods, right? So again, this is related to my book. It's from my book, actually. Okay, so a lot of these concepts, a lot of these problems are in my book. So we're going to look at this improper integral, e to the negative x squared with respect to x. Okay. All right. Is anyone excited for math? Let's make math great again. Put your thumbs up. Let's make math great again. All right. So we're going to look at this integral right here. We're going to integrate that. But before we do, I want to show you what type of function this is. There will be a lot of you who don't know what on earth this is, what type of function e to the negative x squared is. And there'll be a lot of you who do. Hang in there. For those of you who do, I just want to show the ones who've never seen it, how it looks like. Okay. So let's get back. Let me get back to step. I need to, so 1 second, I need to make sure, stop sharing for a sec. Okay, I'm going to share my screen. We're going to go to Desmos. I need to show you graphically how this looks like. Okay, there is Desmos and Desmos. Okay, there's Desmos. Okay, so hopefully you guys can see the type of graph that is up here. Okay, so we have e to the negative x squared. This is what you call a bell curve type of shape. Okay, it turns out a lot of advanced integrals are related to this. So if you see my other videos, you'll see a relationship. Why is he always going back to bell curves? Quite often they are embedded in a lot of integrals. Okay, so e to the negative x squared is a bell curve, right? So this type of shape. All right, now the graph that we're specifically want to look at is e to the whole power of negative ax squared, where a is some parameter in this case. Okay. That being said, what we're integrating, there's already been a parameter in our function. That being said, besides the point, I wanted to show you guys how y equals e to the negative ax squared looks like. So it's a bell curve with some sort of horizontal compression or horizontal stretch, depending on what a is. Okay. All right, so we've got this right now. Now, if we put a slider on the Desmos simulation, okay, if you put a slider on the Desmos graph, you'll see what happens. Okay, so you can see that this proves that there's some sort of horizontal stretch or compression. Does anyone know what it would be? Is it horizontal stretch, horizontal compression, or is it neither? Then explain. Anyone have any ideas in terms of the horizontal effects here? Is it a stretch or compression? Come on, guys, need to cooperate. I want you guys to make math great again. Come on. That's what I'm here for, is to make math great again. Even when it's abstract. Okay, so this horizontal effect here, as you can see, it's going back and forth, horizontal stretch, horizontal compression. That is purely, well, it's not determinate. We can't determine if it's a horizontal stretch or compression. The reason for that is because A is always changing. Okay. Now, to determine a horizontal stretch or compression, it's very simple, right? Okay, this has to do with 1 over A, right? If 1 over A is greater than 1, right? Then it's a horizontal stretch. 1 over A less than 1 is the horizontal compression. Okay, but that's how a bell curve looks like with a horizontal compression. Okay, so it's pretty interesting. It's going to make the slide a bit longer. All right, so let's get, let's get back to it. Okay, so let me stop sharing that. And then we're going to go back and share my screen again. So I'm going to share the entire screen, share that. And we're going to go back to the whiteboard. Okay. So we want to be able to solve this problem. I'm going to do the first one. Okay, so we've got an improper integral of e to the negative x squared dx. Okay, we want to solve that. Now, those of you who already know, you can do it directly using a Gaussian, noticing that it's some form of a Gaussian integral. Okay. However, we want to be able to use what we're doing in this live show. Okay, by using Feynman Trick. By the way, anyone new coming in, just want to let you know that not only is this Feynman Trick day, but you can also send in any integrals that you have trouble with, and I will solve them. Any hard integrals that you've encountered. Anybody, let me know. I'm going to go back and forth. Okay, not at the moment. Okay, so yeah. Okay, so we're going to be looking at solving this guy right here. Okay, now let's go back and see how we can use Feynman Trick. Okay, so back to the definition, right? We know that we have to, we can use Feynman Trick, a method for evaluating differential integrals, by introducing a parameter a, doesn't matter what it's called, I'm going to call it a, right? And then we're going to redifferentiating the integral, because in this case it's an integral, improper integral of e to the negative x squared dx. We're going to differentiate our integral with respect to where that parameter is in our function, okay? And then integrating the resulting similar expression, right? So as you already know, for those of you who are just coming in, Feynman Trick introduced an integral I as a function of a. The integral goes from lower bound x0 to x1 of f as a function of both function of x and the new parameter that you put in with respect to x, right? So in this case, it will be easiest to put a where? Where should I put my a here to use Feynman Trick effectively? Where should I put my a? Come on, guys. Where should I put my a? In the exponent, okay? Now, it may be a bit non-intuitive for some of you. This takes practice. Quite often, mathematical intuition comes by pretty much doing a lot of practice problems. I mean, a lot of problems, okay? But a lot of, they can't just be straightforward problems. They have to have difficulty in them, okay? So you have to do a lot of either intermediate to hard problems. And then eventually what happens is you gain almost like a sixth sense, if that makes sense. Okay. My job is to help you get that sixth sense, if that makes sense. Okay. And quite often, this sixth sense for math doesn't come in easy things like calculations or basic problems, or it comes through like actually hard stuff. Like you have to struggle through problems in order to eventually get that intuition, if that makes sense. Okay, I'll explain. So, improper integral of e to the negative ax squared dx. Is everyone following so far? Okay, so we have that. Now, the reason why I place the a in the exponent and not in front of the e or anywhere else, right, is because if I do it that way, when I differentiate both sides with respect to a parameter a, which I called it here, right, with respect to parameter a, it will, once I do that, you'll be able to see in the next step that it will be easier to integrate the function. Okay, so let me explain. So I prime of a, so that means I'm differentiating both sides with the parameter a, is d by dA, okay, of the integral from 0 to infinity of e to the negative ax squared dx. So everybody following? Come on, guys. Let me know if you're following. It's Feynman Trick day, and it's Ask Me a Hard Integral day, if that makes sense. If you have trouble with any integrals. Okay, so we're still here, right? So we're differentiating both sides with respect to a of the integral. Okay, so again, d by dA of the improper integral of e to the negative ax squared dx. Okay, so that's pretty much straightforward. All right, now the next thing, right? What we can do is, so this is something that you should know. Those of you who are reading like Calculus 1, this is familiar. All of you should have the strong understanding of calculus, right, to do this. Right? But this is very basic. You learn this in Calc 1. All right, so I prime of a is equal to the improper integral of d by dA of e to the whole power of negative ax squared dx. Okay, so as you can see, I moved my operator, the differential operator, d by dA, inside of the integrand. Okay, I'm allowed to interchange the integral with the derivative. That's a rule. There's nothing wrong with that. Okay, you can interchange the position of the derivative with the integral, and vice versa. I can do it back and forth. All right. Any questions? So it's really interesting to see how this method can help us attack complicated integrals. They get more complicated than this, so it's but it's neat that there's multiple ways to. I hope you find it interesting that there's multiple ways to attack mathematical problems. There's not like one. It's not like there's one method fits all. That's nonsense. There's multiple methods to get to the same answer. Okay. All right. So we got this improper integral of d by dA of e to the negative ax squared with respect to x. All right. And as you can see here, right, I get I prime of a. Right. So I prime of a is the improper integral. This is after differentiating. If I differentiate with respect to a, okay, what that means is, now don't get confused. Quite often people get confused. What's the variable? What's the constant? I'm differentiating with respect to a. So what is the variable that is changing and what is constant here? So what is the variable and what's the constant? What's the variable? What's the constant? Well, the variable in this case that is changing is a. That's why when I differentiate with respect to a, it becomes minus x squared e to the power of negative ax squared dx. Okay, so that's why we're down here now. Okay, that's just how we get this result here. All right, after differentiating this portion up here. Okay. All right. Now what we have here is capital I prime as a function of the parameter a is equal to negative. I can move out any constants that are independent of x. So negative the integral from 0 to infinity, x squared e to the negative ax squared dx. Okay. Is everybody following? Put something in the chat. Let's call it Feynman, or F for Feynman. or thumbs up. Thumbs up or F in the chat, just to let me know if everyone's following. Okay. All right, so we got that. So I prime of A equals this integral. Okay. Now, what ends up happening from this is after doing substitutions and after doing lots of the manipulation, you will get down to this answer. I of A is 1/2 all of the square root of pi over A. So all under the square root is pi divided by A. That's the final answer. Okay. I want you, now the reason why I didn't go the extra steps here, I did most of the work here. I know this is an example problem. It's the first time you're seeing me do Feynman Trick. Okay. But since this is a live show, so you guys need to engage with me. I don't want to do all the work. So either for the people who come in right now, okay, try to tell me how I got from I prime of A all the way down to solving for I of A, and how I of A is equal to 1/2 times all under the square root of pi over A, where A is a constant. Oh yes, hi. Thanks so much. Thank you so much. Didn't notice you were here actually. Hi, Poud IP. I hope you're enjoying. What's going on. Yes, thanks for liking and subscribing. I assume that you have interest in mathematics, a background in it. Just let me know in the chat if you can. All right. I'm glad you joined. We're just going to continue doing some more advanced math. Today is integration. It's based off my book, Advanced. Oh, okay. All right. Yes. But you are interested in math. All right. I'm glad to hear that. All right. Again, thanks for liking and subscribing. Hope you watched most of the video. It gets pretty cool. It's really interesting how math can really enrich people's lives. All right, so let's get back to it. So we're looking at integrating this guy, the I prime of A equals minus integral from 0 to infinity of x squared e to the whole power of ax squared dx. Okay. So I sort of skipped some steps for obvious reasons. Okay. And I want anyone else, maybe some of you don't know and you're just interested, but anyone who knows integration per se, there's no excuse. Try and find how I got this result here. How did I get this result? Okay. I'm going to leave it up here. We'll come back to it. If someone in the chat who knows about integration and tackles this and solves it and gives me an explanation, we'll go through it. Okay. And or if anyone after, not anyone watches the live show right away, maybe see it after, please try this for homework, how I get to this result. Okay. Now, again, before getting to this problem right here, the new problem, okay, the improper integral of e to the negative ax with respect to x all over 1 plus x. Okay, so we're going to solve that. That's the next problem we're going to look at. Any questions? Anyone else? Okay, not yet. All right, so yeah, before we're getting to the next problem here, I'm just going to reiterate some stuff. Okay. Okay, so again, anyone who's coming in, today we're looking at open problem night, which means viewers can send in integrals that they have a very hard time with, and or we're talking about Feynman Trick. Okay, so Feynman Trick is a clever trick to evaluate complicated integrals that can't be solved with elementary methods. Okay, so again, Feynman Trick. Okay, I'm going to repeat myself. What is Feynman Trick? It's a method for evaluating advanced integrals by introducing a parameter. That parameter can be defined as any variable. Doesn't matter what you call it, A, B, C, whatever you want to call it. Okay. Once you define the parameter, okay, you're going to be differentiate both sides of that integral that you're dealing with. So you have to d by d whatever, right? D by d whatever with respect to of that integral with respect to that parameter. Okay. And then integrating the resulting in a simpler expression. Okay. So again, right, this is the formal definition. Okay. I as a function of a is the integral from x0 to x1 of a function of x and a. So your parameter is another variable. So you have a function of two variables, x and a, okay, where f is a function of x and a, and dia are continuous. Does anyone know who continuous is? What does continuous mean for anyone else? Anyone else? Today's a slow day. Yeah, today's a slow day. Okay, no problem. I'll continue. Continuity, right? There's no discontinuities in our graph or in our function whatsoever, right? So again, right, let me give you a graph here. Okay, so let's say you had a graph x comma y, and you had a function like this, right? So let's say this over here, and then maybe you had this. So this is a piecewise function. There's obviously some sort of jump or discontinuity here. This would not be a continuous function. Okay, this is discontinuous. Discontinuous. For those of you who have done either like algebra 2 or 3, and or calculus 1, you understand what I'm talking about. So if you have a graph like this, okay, just 1 second. All right, on the eraser. Oh, damn it! I hate when that happens. Undo. Thank God. You have to be careful which eraser you press, otherwise it gives you issues. You can delete the whole thing. Thanks God for that undo button. Okay, so 1 second. So that's a discontinuity. This other graph here, if you look at it, okay, so if you have x, y, okay, this one right here, this is a continuous function. Why is it a continuous function? Anybody know? There's no holes. It's smooth. It's continuous differentiable, right? There's no holes here whatsoever, right? There's no jumps whatsoever. It's completely continuous without any breaks, right? Whereas the other one has holes here. So that's what they mean by continuous. Continuous in both variables. So once you have your formalization, right, you've identified the parameter that you want in your integral, then the Feynman trick states this beautiful equation here, right? Okay. D by dA, right? You differentiate both sides with respect to your parameter A, left-hand side I of A, right? Right-hand side D by dA of the integral of f of x, comma a with respect to x. What you do to one side, you do to the other side in mathematics, right? That's how everything works. If you operate on one side, you have to operate the same on the other side. Otherwise, the equation's not balanced. Okay. So yeah, Feynman trick is the flavor for today. And or anyone who wants to jump in and give me hard integrals that you've been stuck on. Right? It doesn't matter. Give me a hard integral because I like integrals. All right. So yep. So don't be shy. Viewers can send in complicated integrals. This is why I have water. You give lectures, this dries your throat. Okay, so let's get back to it. So there's no complicated integrals coming in. I will come up with a complicated integral. And it's the one from my book, actually. It's this guy right here. Okay, so we're going to be solving this integral. I as a function of a is equal to the improper integral of e to the negative ax power with respect to x all over 1 plus x. Okay. This is a nasty one. I pulled it out because this will challenge even the guys who are really good at integration. So for those of you who have a background in integration and linear algebra, this lecture is for you. And for two types of people, right? You want to maybe build on your integration by learning more methods. Okay, it will help probably in your classes, like if you take calculus 1 to 3, um, also complex variables, and anything to do with numerical analysis. Um, yeah, my lectures are for that, especially since they're linked to my book as well. Okay, advanced integration techniques. All right, so we're going to be looking at solving this guy right now. Okay, so this improper integral. All right, so I'm going to let you guys soak that in. If anyone's in the chat who wants to take a guess how to solve this beast, this is a nasty one. Yeah, this is nasty. But I like to hear your thoughts on how to solve it. Those can be in the chat. Let's just see. Okay, not at the moment. All right. Don't be shy. Just come in and ask questions on integration. If you have any particular problems that you have at the moment with integrals, maybe you're stuck in class or it's for homework, or you want to learn about Feynman Trick, you want to learn about interesting integrals or sums, this is the place to be. I'm going to help you get your math on. All right, so, and particularly Feynman Trick. Okay, so we're doing Feynman Trick today. Anyone who new coming in, we're going to be looking at Feynman Trick, how to evaluate an advanced integral that can't be solved by elementary methods. This is one of the ways to do it, is Feynman Trick, introducing a parameter A. Okay, so yeah. All right, so we've got this this integral, this improper integral right here, right? Again, e to the negative ax power with respect to x all over 1 plus x. Okay, so we want to be able to solve this. Now, yes, you can say that Feynman trick here has already been applied. What do I mean by that? Already there's been an input of the parameter. Okay, so we have, it's a function of two variables, x and a, where x is a function that we already know, variable already, that's already changing, but a is also another variable. In this case, a is the parameter. So since it's a function of two variables, already Feynman trick has already been used in this problem. So you don't actually have to determine where to put the parameter. So that's the easy part. Okay, so the way I've set up this question for my book is I've already given you something to work with, right? Knowing where to put the parameter. If I haven't given you the parameter, and then you would still have to use Feynman trick, and you'd have to guess where the parameter. You have to figure out where's the correct placing of where that parameter goes. In order when you differentiate both sides, you'll be able to integrate after correctly. Right? And that would have been very hard actually, because what comes next is actually very complicated. Okay, so I had to have for this problem, I had to have already, let's say, giving you a helping hand by already telling you, no, that's where we're placing our parameter, right in the exponent. Okay. All right. Okay, so that's what we're going to be looking at. Just waiting. I want to see if anyone else is coming so far. Yeah, it's been a bit slow. Let me see. No, not so far. I'm just waiting for some people to come in. Don't be shy. We're looking at today's very unique night. We're going to be discussing Feynman trick, a way to combat complex integrals. If you're ever stuck on integrals, you're like, oh wait, I can't integrate that problem. This is a new technique for, I know, a lot of people. Also, don't hesitate to stop me in the middle of me talking, because this is also like an a hard integral night, right? So any problems that you have per se, any integral problems that you just had trouble doing, again, I'm going to help you do it. Just send me the problems in the chat. Just send me the problem that you're working on. I'm always going to be referring back. Okay, nothing yet. All right, so again, this for anyone who comes in, I'm going to help anyone who has trouble. It's free help, nothing at all. If you have trouble with the complicated integrals and you don't know how to solve them, I can give a lending hand. Yeah, just once again, send anything in the chat. In the meantime, we're going to be looking at how to solve Feynman trick integrals, right? All right, so I'm going to continue. So looking at this integral, the improper integral of e to the whole power of negative ax with respect to x over 1 plus x, it already has a parameter a in the exponent. Okay, there's already some parameter here. All right. And the way to do this, even though it has a parameter a, this is going to sound slightly counterintuitive, is even though I use Feynman trick already by using a parameter a in the question, that's all we're doing for Feynman trick. I don't need to differentiate both sides. Differentiate both sides is implying Leibniz rule for integration, which is a must for Feynman trick, but it's not necessarily needed for this, right? Because if I differentiate both sides, I'm going to make my integral more complicated and it goes nowhere. Okay, so Feynman trick, you don't need to introduce the parameter for the integral. That's it for Feynman trick. We don't use the Leibniz portion where we differentiate both sides of the integral. That will make things more complicated. Okay, so you have to be able to intuitively know what to use, when to stop, what method to use, how to manipulate things. Again, that is called mathematical intuition. Okay, and it comes through doing a lot of problems, a mixture of intermediate to difficult problems usually. Actually, I have to be honest, the harder the problems, the better. It strengthens the intuition. Not to say that it won't be very difficult. It is very difficult. But I can't sugarcoat it. Anyways, let's continue. So if we're not using a Leibniz method to finish this integral off, what method are we using? A form of U substitution. Okay. And the U sub I'm using is I'm letting U equal to a times 1 plus x. Anyone have ideas why I did that? Nobody. Well, the reason why I did U equals a parentheses 1 plus x, first off, it looks like, for those of you who don't already know, like an exponential integral. Intuitively, it doesn't look quite, but it looks somewhat like an exponential integral. So I have to manipulate my U substitution to head towards that, if that makes sense. Okay. For those of you who don't know what an exponential integral is, okay, any integral in this form, the integral from e to the x over x dx, right, is equal to ei of x, that's an exponential integral, plus c. The plus c is there because this is an indefinite integral. But any integral of e to some function of x divided by that function of x with respect to x is called an exponential integral. Okay, and you can see what we have here almost looks like that, but not quite. The a and the 1 plus x is an issue. Okay, but you can see it's something like that. So my thinking is telling me that I may need to use a u substitution first off, and then let u equal to a parenthesis 1 plus x. Okay. Because the 1 plus x, if I let that equal to a single variable, you think of it as being our x, or whatever you want, u in this case. In other words, I want to compress the integral to a form that is mathematically known due to known formulas and definitions. Okay. All right, so let u equal to a parenthesis times 1 plus x. Then my du has to be a dx. Okay, because if I were to multiply this in, this is a, and this is ax. If I differentiate with respect to x, a is gone, a is a constant. Differentiate ax would just be a, because x would be gone. So it's a dx. Right? If anyone understands, thumbs up in the chat to let me know that you're understanding. I need to make sure everyone is on the same page. Thumbs up, thumbs up. Anyone in the thumbs up? Thumbs up, please. Okay. All right, so that's what we have. So our u and our du. We have our u and we have our differential. Okay. Now, the next thing we're going to be doing, okay, is we're going to start multiplying in. Okay. Why? Why should I multiply this? Why should I multiply my a inside the brackets? I'm just waiting for anyone else. Taking my time. I don't go too fast like when people come in. So I'm just multiplying in my a by 1 plus x. Okay. There's a reason why. Because if I'm using u substitution, remember, I have to replace all of my x's with u's. Okay, so I could replace the denominator to some degree, even though it looks a bit awkward. Okay, so I have that, you know what I mean? I can have a u over a. Would that be correct, though? If I solve for 1 plus x in the denominator with u over a, would that be correct? Because remember what I said, we need our integral to be a function of u. Okay. No, actually, it's incorrect. If I had done u over a, divide both sides by a, solve for 1 plus x, substituted in here, that would have been incorrect. Okay. The correct way to do this is use that u and multiply a inside. Okay. So u equals a plus ax. Why am I doing that? Okay. Because just how I found my du as a dx, so I can replace my dx, I need to replace my x in terms of u. So if I multiply in u equals a plus ax, I'm going to rearrange for x as a function of u. Okay? But the only way to do that is to multiply in first, collect terms, rearrange, and then solve for x. Okay? Does that make sense to anybody in the chat? All right, so look, right? So u equals a plus ax. I solve for ax. So ax is equal to u minus a. Subtract a on both sides. Okay? Now from this, I need to solve for x. I divide both sides by a. So x equals u minus a all over a. Okay, like this. So u minus a all over a. All right. Now, that's my x. Therefore, if I did dx, I need to find my differential. So dx is 1 over a du. How do I know that? That's from earlier. If du is a dx from our original function, after taking the derivative, the solve for dx will be du over a. So we now know what x is as a function of u, and we now know what dx is as a function of du. Right? Well, I hope everyone is understanding. Okay? I'm just going to refer back and make sure everyone in the chat is either understanding. If you're not understanding, let me know in the chat. And for new people coming in, if you have calculus questions, specifically integration, that you're finding a hard time, ask me, and I can help. Okay. All right. So let's continue. So we have our x, we have our dx. Okay, so we have our x expression, our dx expression. What do we do with that? What do we do? We resubstitute x and dx back into our integral. Okay, so into our Feynman Trick integral. So I, as a function of a, was initially the improper integral of e to the negative ax power with respect to x all over 1 plus x. Okay. And we start inputting everything as a function of u. Okay, now be careful. Everything has to be a function of u. And even the limits of integration have to be in terms of u. Can anyone tell me how this integral became from 0 to infinity to now infinity to 0? Anybody know? How did this integral down here switch from 0 to infinity to 0? Well, the reason is clear, right? Look up here. If u is equal to a plus ax, right? Remember, x was from 0 to infinity. Okay? X was from 0 to infinity. So if I input the upper bound, right? Upper and lower bounds. Okay, let's start with, so let's start with infinity, right? So x is going from 0 to infinity. So if that's the case, in order for that to happen, right? So let's say over here, 0 infinity, x is infinity. Let's say starting off with this bound here, putting x being infinity. So infinity equals u minus a. Okay, so infinity equals u minus a. So what would have to be in the denominator? It would have to be 0. A would have to be 0, right? Okay. So divided by 0. So what ends up happening is, let me just put it this way. I think that will confuse people. Okay, so let me just get rid of that. Right. So as I said, our integral, right? Our integral went from 0 to infinity, right? So from 0 to infinity, from infinity to 0, when it's a function of u. Does anybody know? Anyone new in the chat? Okay, not yet. So the reason for that is, look over here. What did we define u as? Our u substitution was this, u equals a plus ax. Okay. Well, if x is infinity, u is infinity, right? If x is infinity, u is infinity. If x is 0, okay, what happens when x is 0? In order to get x is 0, so in order to get x is 0, let's use this actually. In order to get x is 0, what does u have to be? So think of it this way. U minus a over a is equal to 0. X is 0, right? Well, in that case, u minus a is equal to 0. U equals a. Okay? So one of the bounds has to be a. Oh, sorry. It's not from infinity to 0. It's infinity to a. Yes, I found a mistake. So upper limit of integration has to be a. Okay, so now it's a. So it's infinity to a. Okay. Any questions so far? Anybody have any questions? Put something in the chat, maybe thumbs up, or let me know where you're having an issue. Anyone having an issue so far with this integral? Okay. So again, as I was saying here earlier, right? To get the limits of integration, right? Remember for x, it was going from 0 to infinity initially. okay? This was going from 0 to infinity. That's for x. But we know that x, right, on the side here, x equaled u minus a all over a, right? So starting at infinity, if x is infinity equals u minus a over a. If I solve for u would have to be infinity, okay? Right, so u is infinity. And then when x is 0, right? And so that I did the upper bound. And the lower bound, right? When x is 0, 0 is equal to u minus a all over a. To solve for the lower bound of u, right? Therefore, u minus a is equal to 0. Solve for u. So u equals a. So our upper and lower bounds are infinity and a, if that makes sense. Okay, just let me know if there's any questions. So my new limit of integration is actually going from, from a to infinity to a. All right. All right, so there's no questions. I'll continue. Okay, so now we just substitute, as I said, everything earlier. Everything in terms of x as a function of u, everything in terms of dx as a function of du. Substitute into the integral. So e to the negative whole power of a, parentheses x was u minus a over a. Okay, dx was 1 over a du. I put that in over here. Okay, so we have that. Right, and then in the denominator, it will be 1 plus, on parentheses, u minus a over u, because x is u minus a over u. U minus a over a. So be careful. U minus a over a. Okay. That's what we found up here. X equals u minus a over a. Okay. Let me erase this. Don't have this on the side that are annoying. See if everyone in the chat is okay. Okay. All right. So let's continue. Okay. So we've got that. Now that we have this information, we can get into we substitute all that information in again. So again, anyone new coming in, don't be shy. If you have any hard integrals that you need help with, I am here to help you with any advanced integrals. Okay, maybe you're stuck in class. Maybe you don't know what approach to use, what method. Tonight is a very unique night. I'm giving help on complicated integrals. Okay, so if you have any calculus homework that you're having trouble with, send it my way, please. At the same time, during the lecture, I'll be doing some interesting Feynman Trick methods. Okay, so yes. All right, so we have all this information. We have our limits of integration for u. We have our new u substitution as function of u in our integral. Okay, all x's have been replaced with u's. Okay. All right, so we're going to the next page. And now what we're doing as a continuation, right? Integrate from infinity to 0. Okay. This is going to be e to the negative. Now, as you can see here, the a is canceled. Look very carefully. Okay, so from page 2, these a's are going to get canceled on the next step. It's because a divided by a. Okay, so that's what I did in page 3. Now it's this integral of e to the negative power of u minus a times du over a. Okay, remember a is a constant here. That's our parameter that we used. All right, and then we're dividing the whole thing by 1 plus u minus a over a. Okay, so by 1 plus u minus a over a. Okay. So then from here, the next step, all right, shouldn't be, let me see here. Just want to be careful with something. Shouldn't be a negative, not from what I'm seeing. Yeah, let me be careful with that. Yeah, there's no negative there. We said infinity to a to infinity. Was it a to infinity? Yeah, I think it was a to infinity. Let me be careful with my limit of integration. I'm going to go back and double check something here. X equals u minus a over a. Limits of integration were from 0 to infinity. So on the higher limit of integration, x is infinity, x is infinity. X is infinity. U has to be infinity. Then for lower limit of integration, when you have 0, okay, 0, that means that u equals a, right? Because that means x equals 0. For limit of integration, solve for u. So u minus a over a, multiply both sides by a, u minus a is 0, u equals, yeah. So for integration will be limits of integration from a to infinity. That's where the mistake is. Okay, so careful, a to infinity. Yeah, always be careful with your limits of integration. Not a infinity. Yeah, like this. Lower limit a, upper limit infinity. Okay, lower limit over here. Okay, so lower limit, again, this is going to be a, sorry for that, a to infinity. Okay, so yes, so that's what we had here. Okay, 1 plus u minus a over a. The next step here, 1 over a, I moved out the 1 over a. That's a constant, moves to the front. It's independent of u. Okay, anyone else in the chat? Thumbs up. We're making advanced math great again. Couldn't help it. All right, so we got 1 over a, the improper integral, right? E to the whole power of negative, parentheses u minus a, with respect to u, right? I mean, with respect to u. All over 1 plus u minus a over a. I think that's straightforward. A is a constant, came in front of the integral. Everything else is just simplified, okay? All right, so that's step 2. And then step 3, there's no negative. Not that I'm aware of. Let me be careful. Yeah, there it is. Because I have to flip the integral. I'm making a stupid mistake today. Yeah, so over here, this was going from infinity to a. Yeah, infinity to a. That means that this would have been a negative. So this would be, I moved the 1 over a to the front because it's a constant. Then this becomes negative in order for me to say, oh, I'm going from a to infinity, right? Because for those of you who know, you should know because you've taken this lecture is for people who have a background in integral calculus, right? So if you have integral calculus background, you'll know what I'm talking about, right? So over here, right, there's a theorem that states that if you take the integral from a to b, right, this is equivalent to negative the integral, right, from b to a. Okay, that's all I'm doing here to make it more efficient. So it's negative 1 over a integral from a to infinity of e to the negative u minus a du all over 1 plus u minus a all over a. Any questions? All right, nothing yet. Okay, so we're going to continue. Again, anyone new coming in, if you have any integral problems, you can interrupt me. You can ask me questions. It doesn't have to be on what I'm doing right now. It can be any hard integral, really hard integral that you find and you need help. I'm here for it. Okay, so negative 1 over a integral, we got that part. Step 3 now is to notice that from here, right, the 1 over a, right, so 1 over a can be multiplied by the integral. That's, say, a down here. This would be an a. Yeah, my mistake, 1 over a. Now, that negative came in the front here. I'm going to explain because I can distribute the negative anywhere. It's the same thing as saying in the denominator, right? Whether it's in the front of the constant or down here is the same thing. So 1 over a, integral from a to infinity of e to the whole power of negative of u minus a du, right? All over negative, in parentheses, 1 plus u minus a all over a. I have to put all parentheses here because we have a negative you're distributing after. Okay, and then from the next step, I'm just distributing, right? So distributing, filling in. So this will now be 1 over a, and then I integrate from a to infinity of e to the whole power of negative u minus a with respect to u, divided by, coming inside, that's a -1, coming inside again. This changes because this is going to be negative all in parentheses of u minus a. I get a minus u over a. Please stop me if you either have questions on this or your own homework questions. Come on. Show some love for the channel. Come on. Thumbs up in the chat, please. Thumbs up, thumbs up. Thumbs up in the chat. Okay. All right, so as I mentioned, we're on to step 4 now. This is over here. Okay, I mean step 4, I mean down in this next part here. So 1 over a integrates from a, that's an a again. It's 0. That was an a. So integrate from a to infinity, e to the whole power of negative u minus a with respect to u. Okay. Now, this is easy. That -1 transformed into negative a over a. Right? I need to get a common denominator because it was 1 over 1. A common denominator to add them. So multiply by a, and then collect like terms over a common denominator. Okay, so I had to get the negative a over a plus a minus u over a. And then collecting the like terms, the a minus a will cancel, and this is minus u over a. Okay, so that's why in the next step here, this is the next step. I now get 1 over a integrate from 0 to infinity of e to the whole power of negative parentheses u minus a with respect to u divided by negative u over a. Any questions? Anyone have any questions? Okay, looks like nothing yet. Just need a drink of water. Yeah, sometimes your mouth can get dry if you keep talking, especially in a lecture. All right, so you have that. Then from the next step that I have highlighted in white, okay, this is 1 over a improper integral of e to the whole power of negative parentheses u minus a du all over negative u over a. Okay, because the a's got canceled. Right, it's on this step here. Okay, next I am going to flip because that's divided by negative u over a, so flip it simple. 1 over a improper integral of negative a over u times e to the negative u minus a with respect to u. Okay, that should be straightforward. How is it straightforward though? Well, I'm dividing by a fraction. I'm flipping it now, right? So now my a will cancel, right? So that's very straightforward. Okay. Actually, in the next step, I don't even show that yet. I sort of rushed it. So the a's will cancel. Okay, so where is it? Well, yeah, I moved the a to the front, minus a over a. There's no minus, by the way. There's no, because that minus was omitted. Get rid of this. It's supposed to be saying integral from a to infinity. A to, I hate when I make these minor mistakes and they happen. A to infinity, yeah. A to infinity. Yeah, lower limit is a, upper limit is infinity. Yeah, there's no minus here either. Yeah, get rid of the minus. Yeah, a over a. This is a over a. And then we get an improper integral here of e to the negative all in parentheses of u minus a with respect to u, all divided by u. Okay. Again, this should be here. Lower limit should be a. Little a. Okay. Any questions? Anyone have any questions? Let's see. I had someone earlier to ask something, but okay, so nothing at the moment. All right, so let's get back to it. Again, there's no negative. And that lower limit of integration should have been a. Okay, so again. So now we're left with, because the a's will cancel, a raised 1. So integral from a to infinity of e to the negative, all in parentheses, of u minus a with respect to u all over u. Now I can do something interesting. Okay. What can I do here? Remember, the a is a constant. A is a constant. Everything is as a function of u, not a. It's a function of u, not a. So how did I get e to the negative u times e to the a? How did I do that? Anyone know? Anyone know at all? Well, I just used basic exponent laws, right? All I did was, if this is a base raised to 2, raised to an exponent that's been added or subtracted, then it's equivalent to having the same base multiplied by each other is equivalent to adding their or subtracting their exponents, right? So e to the negative u times e to the a du over u. There's no negative here. No negatives. No negatives. Okay. And lower limit of integration should be a again. There's no zeros. Okay. So I can move e to the a to the front. It's independent of u. There's no function of u. So I can. It's total constant. E is a constant. A is a constant. So e to the a. Okay. So it should be e to the a times integral from a to infinity. Integral from a to infinity of e to the negative u du over u. Okay. So as you can see, we're making things. This is the reason why that u substitution worked, because you have to see quite a few steps down that you're going to make the integral that you started with much more simpler. That's how you know you're going the right step. Because if your integral becomes more simpler, or what I like to call more beautiful, if that makes sense, then that usually tells you you're in the right direction. If your integral becomes much more complicated, way more nastier, more likely it's incorrect. There are special cases, but more likely it's incorrect. There's going to be problems. Let's get more water. Okay. All right. So let's continue here. Okay, so we have that. Then the next thing is to take, this is an improper integral. Okay, this is an improper integral because it's the infinity. That's an a again. Okay, so limit, I'm creating a t dummy variable. Okay, limit as t approaches infinity of the integral from a to t of e to the negative u du all over u. Okay. There's no negative here. Okay, that's just e to the a, limit as t approaches infinity of ei as a function of u from t to a, right? So t to a. Careful here, some mistakes. Might need to make calculation. Right, because this is an exponential integral. I talked about what an exponential integral is, in case for those of you who didn't know earlier. Okay, it had to me. An exponential integral is this. The integral of e to the function of x over the function of x dx is equal to e, capital EI, as a function of x plus c. So when you take an exponential function divided by x and you integrate, that's an exponential integral. Okay. So then this is just e to the a. This is not negative. A limit as t approaches infinity. T goes to infinity, so it's be 0. Yeah, because you have to take the upper limit of integration. So EI of t, this would be like this. Sorry about that. Let me just erase something. This should be like this. Just 1 second. Ah, damn it. So let me get to the desktop again. See if anyone is in. Anybody's in. Okay, so I was saying something here. So limit as t approaches infinity. Okay, and then we had this would be square brackets. I'm going to say e exponential interval of ei of t, right? Because upper limit of integration minus lower limit of integration, ei as a function of a on square brackets. Okay. All right. Then from here, what's it end up happening? So it's using fundamental theorem of calculus. So ei of t now, right? Now t is approaching infinity. Now think of this carefully. This is an exponential integral function. Okay, so ei of t. Okay, remember that ei of t is a function that's an exponential integral function. So if t approaches infinity, what will happen to ei of t? Ei of t, what happens? Nobody knows what happens to ei of t. Guess what happens to ei of t? What ends up happening is that since t is approaching infinity, if we draw, that's why I like to always do this. Drawing stuff helps make sense out of equations and problems. So let me do this. So we have this graph here. Okay. This is t. This is ei of t. Ei is a function. Yeah, ei is a function of t. What will end up happening, since it's an exponential, remember it's e to the negative x. So e to the negative x over x. We'll have something like this happen. This is the exponential decay. Okay, because anything e to the negative x power is something like this. Okay. So since we have something like this, it's going to become asymptotically decreasing here. So it's going to be exponential decay. And as t approaches infinity, right, this is going on forever. So as t goes to infinity, right? So as t approaches infinity, ei of t has to approach 0 because this is approaching the t-axis. It's not hitting the t-axis, but it's approaching the t-axis, and the t-axis is at 0. So as t approaches infinity, then what ends up happening is that the exponential integral function ei of t has to approach 0. So that means that this goes away. This is approaching 0. Okay, so then I'm just left with minus ei of a. So minus ei of a times e to the a. So the final solution to this integral, the improper integral of e to the negative ax power dx all over 1 plus x, is minus e to the a times the exponential integral as a function of a. And we are done. Yay. Okay, so that was too much actually, even for me. Okay, so that's how we able to get that result there. As you can see, very little of Feynman trick was used. Okay, so the hardest ones aren't the ones that need to use Feynman trick every single step. The hardest ones are the ones that require you to think creatively and use the strong intuition. Right? Know what technique to use, know what approach to use. Okay, so you have to be able to distinguish which approach is the most helpful and ones that just don't make any sense whatsoever when you're using them. Okay. Any questions? All right, so we still have time left. One of the last things we're going to be discussing is something called complex-logarithmic substitution. Okay, I'm not going to go into detail here. Maybe in the office hours on Friday, we'll go into it more. But we're going to discuss this. Okay, so I have to give you a definition of what a complex logarithmic substitution is. They're handy in solving integrals that look, again, look weird. Now, you have to be able to distinguish which technique to use, right? Because it's like with Feynman Trick, you have to use it for certain types of advanced integrals, okay? Now here, you're going to use it specifically what I wrote down for the definition. By the way, any questions on what I did earlier? Any questions? Know if there's any questions. Okay, so no questions yet. All right, so we're looking at complex logarithmic substitution. Okay, so what is it? So I wrote down a definition. Okay, so a complex logarithmic substitution occurs when you take an interval, right? An improper interval. It has to be an improper interval, by the way. So improper interval of a logarithmic function, okay, over a rational function, right? So anything in the form, I mean rational function, you should know what I mean. I mean anything of the form of f of x over g of x, something of this form, okay? And, you know, rational functions can look something like this, right? Maybe asymptote something like this if you're forgetting, and maybe you have a graph like this that's asymptotic to this part of the graph. Another one here that is going to be asymptotic. Another one over here, asymptotic again. Okay, so something like this would be a where you'd have to use, you know, logarithmic substitutions. Okay, as long as you have a logarithm divided by a rational function, that's when you use it. So complex logarithmic substitutions occur when you take the integral of a logarithmic function over a rational function, especially when the integrand is a complex term. Okay, what do I mean by that? We're going to go all the way over here. Okay, and it's represented by the following. Okay, so it's going to be log. Okay, so log of z equals ln of z plus the imaginary part of the argument of z. Okay, so z is a complex number, right? So complex numbers a plus ib. For those of you who already know or don't know, you should know what a complex number is. A plus ib, right? Just to give you a little bit formalization here, just some review if you forgot. Complex number on an argand diagram has a real axis, the x-axis, imaginary axis on the y-axis. Okay, let me know if anyone is getting lost or no. Thumbs up in the chat if you're all following. If anyone's following. All right, so yes, we're going to continue. So we have the imaginary part, we have the real part, okay? Now the real part, okay, so the real part is, you know, the real numbers, imaginary is the imaginary part, okay? And usually we have something like this, okay? When it comes to our Venn diagrams, complex numbers behave like vectors. So if I start at the origin, let's say at 0, 0, okay, and I have a point at the origin of 0, and I extend my origin to maybe some other point P, maybe this is point O, the imaginary number is located, the coordinates are located at A, comma B. Remember that Z is equal to A plus IB, where A is real. I said highlight. It's okay. Yeah, this is real, and this is imaginary. That's real. This is imaginary. Imaginary as a function of z. Real as a function of z. Okay. And the argument of z is just the a non-zero number that is going from the positive real axis going counterclockwise in terms of an angle. Okay, so you have the argument of z, if that makes sense. Okay. Refer to your notes. I won't go into it that much. I expect you guys to know complex numbers, and I'm going to go into this. Refer to your notes or past classes on complex numbers. Okay. So here's an example problem that I'm going to leave for homework. Okay. I'm going to leave this to see if you guys can figure out how to do it based on the theory alone. Okay. Quite often when people teach math, they either have, definitions, theories, or formulas. And then after they go through it, they give examples and stuff like that. Okay. I also do that to some degree. However, though, I'm going to make it more challenging. I'm going to show you as we go on in our lectures, actually, I'm going to show you definitions and theorems and so forth, new definitions and theorems, depending on what section we're on. But I'm going to give you guys to work on the examples for the very first time without me doing it. Okay? Because I feel that will help you guys facilitate some sort of creativity process. Okay? Not to say that you can't learn about me doing that, and then after showing you the example, and then you go through it, I go through it, and then I finally give you an example. But I want to strengthen your skills here. So I feel like I'm going to show you the theory. I'm going to go through the theory, explain it well. We're going to rigorously dive into it. You ask me questions back and forth, if there's anyone here, obviously. I just want to make sure if anyone is coming in tonight, and it looks like no. Okay, but that's how I'm going to start doing things from now on. Okay, and then I'll give an example problem and see if anyone can actually do it. I'll do part of it, but I'm going to leave holes. And those holes are meant not to frustrate, but to actually help you, to get you guys actually engaged in the content. Okay. So let's look at the problem. We have to have an improper integral of log z dz all over 1 plus z squared. Okay. Hint, hint. I'm starting this off. We have an improper integral from 0 to infinity, ln of z plus I times the argument of z. As I said, we're using this substitution here. Okay. Because we're dealing with a logarithm as a function of the complex number z over a rational function. Okay, so that's why I did that. So that tells me I have to do something like this. Okay, now I left the next step unanswered. Not to say that it doesn't have an answer. This is your homework. So whoever's watching this after, or if anyone else is watching, please do this for homework. I will put this in red blocks, in square brackets, pun intended, because everything in math is square brackets or parentheses. Homework. All right. Homework. Do this for homework, right? Figure out the rest of the integral, and hopefully there'll be people who come on Friday who see this. My office hours are 7 p.m. Eastern time. Hopefully you can go through this if anyone is on. Share me your solutions to this problem. And if nobody knows, or if nobody did come on, or anyone did it, I'll go through this specific problem as well. Okay. All right. So that's the homework. And one other thing. No, I can't think of it. Since not that many people came today, I can't really give any other homework. Unless people see it after. I mean, I can always, haven't really thought of anything else. Okay, that is it. Yes, that is more likely it. All right, so that is it for tonight. I'm getting a bit tired as well. It's always been a pleasure teaching you guys. Again, STEM Online Academy is here to help you build mathematical intuition by learning complex techniques in advanced mathematics, physics, and engineering. We hope to either improve and challenge undergraduate students taking mathematics. like and subscribe to the channel, please. It would be very handy. Also, if you are interested in learning more on integration or calculus in general, you can either contact me for tutoring lessons. I'm always available, right? One-on-one help. One-on-one help is the best, especially when it's personalized, because I can focus on an individual's needs, especially if conceptually they're having a hard time and they need help. So tutoring is one thing. And or if you want to learn yourself, but you need a reference, my book, Advanced Integration Techniques, is always available. It will be put in the description below for this live show. Okay, both descriptions, both links will be put in the description. Okay. Have a good night, guys. I'll see you. I think I'll see you next time. We'll be on Friday. So Friday will be another live show, specifically. Yeah, it's office hours. Okay, so office hours, and yes, that will be it. Okay. Again, like and subscribe. Have a good night, guys. Okay. Bye-bye.